Hello everyone. In this video we're going to be solving a differential equation that never ends. We have y equals y prime plus y double prime plus y triple prime, so on and so forth, all the way to infinity and beyond. So we have this infinite differential equation. How can we solve it? We're going to talk about two different solution methods, even though one of them may be incomplete. So let's go ahead and start with the first method. For my first method, I want to go ahead and use a power series for this. Most equations can be solved easily with power series. The problem is it's hard to sometimes convert it to a well-known function. For example, we can write power series for y equals e to the x, or tangent x, or arc cosine x, or any other function like square root of x. But if we're given a series, finding out what that represents as a function could really turn out to be really hard. But let's go ahead and see if we can use it anyways. So we're going to assume that y can be written as something like this. A sub 0 plus a sub 1x plus a sub 2x squared. In other words, a power series is an infinite polynomial, okay? And because it's an infinite polynomial, it can represent pretty much any function. So let's go ahead and start with this, but using the sigma notation might turn out to be a little easier. So let's go ahead and also write the same thing with sigma. Sigma is the summation symbol, as you should know. So let's go ahead and start with n equals 0 to infinity of a sub n x to the power n. So if you replace n with 0, you get the constant term, and n equals 1 gives you the linear term, so on and so forth. Make sense? Okay. Now, once we have this in sigma form, we can go ahead and differentiate it easily. One thing to keep in mind though, when you differentiate, the power reduces, right? So you kind of have to change the index. Make sense? You're not going to have anything with n equals 0 anymore because that is a constant term. Its derivative is going to be 0. Make sense? So let's go ahead and start with the first derivative. For example, the first derivative of this in sigma notation would look like this. You're going to go ahead and use the properties of derivatives. So we have a power or a polynomial. You're going to go ahead and bring this to the front. It's going to be with the sigma, of course, n times a to the n. And then, of course, the next thing you need to do is the reduce to power by 1. So the next one is going to be x to the power n minus 1. And like I said earlier, n does not equal 0 anymore, because if you replace n with 0, you get something weird, which is x to the power negative 1, which is something that you don't have. So you have to now jump up to 1, okay? And every time you differentiate it, you're going to have to change the index, okay? Bump it up by 1. Of course, infinity is not going to change. This is the first derivative. And what are we going to do next? We're going to do the second derivative. But before that, let me go ahead and acknowledge where this problem comes from. Thank you, Anderijal 9033 for this beautiful suggestion. Great, so let's go ahead and see how we can use this derivative, and I'll probably take this expression right here, being lazy here. I'm going to go ahead and move it over here so we can go ahead and work with that, okay? Here we go. That is my, where does that n minus 0 come from? Forget about it. We're going to go ahead and differentiate this one more time to get the second derivative, and maybe I'll do one more time to get the third, so that we can get a consistent pattern, hopefully, right? So when we differentiate one more time, we're going to lose the index. Remember, it's going to start with 2 now, 2 to infinity, and now you're going to bring this to the front, as you know the properties, n times n minus 1, and then a sub n, that's a constant, so it's always going to stay, but the power is going to be reduced and become n minus 2. You see, it's not that hard if you know the rules. And the third derivative, y triple prime, is going to be n equals 3. So you can kind of tell the first derivative starts with n equals 1, the second starts with 2, third with 3, and so on and so forth, okay? Now we're going to bring this one last time, n minus 2. It's going to look like this, n times n minus 1 times n minus 2. And we're going to have the a sub n again. All these are constant. Of course, I mean, a sub n is not a constant, it's the nth term, of course. It's kind of like a constant, but a variable at the same time, x to the power n minus 3. And this is expected, right? Now, what are we going to do with all this information, right? We're going to plug it into our equation. What was our equation? Y equals y prime plus y double prime plus y triple prime, so on and so forth. And you can do the third, fourth, fifth, however much you like, but I wouldn't really do that much if I were you. Now let's go ahead and replace y with what it is first. What is y? Y is the original, remember? It is sigma n equals 0 to infinity, a sub n, x to the power n. Great, this is y on the left-hand side by itself. And then we're going to bring in the y prime, n equals 1 to infinity, n a sub n, x to the power n minus 1, plus n equals 2 to infinity, n minus 1, a sub n, x to the power n minus 2, and let's see if we can fit it over here, plus n 3 to infinity, n minus 1, n minus 2, a sub n. You get the idea, hopefully, right? Or I could do this instead of just scribbling that. Let's go ahead and write it down here because we don't have enough room, plus n equals 3 to infinity. It's going to be n minus 1, n minus 2. But notice that there are 3 consecutive terms here. That way you can tell you're doing n equals 3, so they're all consistent. N to the power x, x to the power n minus 3, and then, of course, this will go on forever. Okay? Good so far? Now, here's our goal. On the left-hand side, we have a single expression with sigma, right? So on the right-hand side, we want to do the same thing so that we can compare the coefficients. Because if you have two infinite series, think about it. If you have two infinite power series, their coefficients have to match by power, right? So the coefficient of x to the power 0, which is a constant term, they have to be equal. The linear term, they all have to be equal. Hopefully that's going to give us a pattern which we can use. Now, how do you go about simplifying the right-hand side though, right? Well, here's one thing we need to be careful about. First of all, you do need the same power so that you can kind of bring these together. But also there's another requirement, which is the indices have to be the same. If you have two sigmas with different indices like n equals 1 to infinity and 2 to infinity, you can't just add them. They have to be the same. Make sense? So in order to do that, we're going to expand 2 terms here and 1 term here so that they could all start with n equals 3. Hopefully that's going to give us a pattern. Here's how it goes. You start with n equals 1, infinity, and a sub n, x to the power n minus 1. Here's what you need to do. You basically need to bump it up by 1, right? So instead of n equals 1, you need like n equals 2. So replace, and here's the trick to do that. Replace n with k minus 1 and do it everywhere. When you do it, you're going to get the idea. It's going to start with k equals 2 because k minus 1 equals 1 means k equals 2. But here's the problem. You don't want k. You want everything to be n. So we're going to do the following. Instead of replacing with k minus 1, we're going to replace n with n minus 1. And this is okay because you're not saying n equals n minus 1, which is impossible, right? You're just saying, hey, we are using substitution. So replace n with n minus 1. That gives you n equals 2, right? And then here, n with n minus 1, n with n minus 1, and here n with n minus 1. And this is what you get from here. You get n minus 1 equals 1, which means n equals 2. The sigma is kind of weird. Let's make it again. To infinity, of course, this infinity is never changed. This is going to become n minus 1, a sub n minus 1, x to the power n minus 2. Now, do you think these two can be added? Well, we have to do it one more time, but just think about the first two terms. They both start with n equals 2. Yes, we can add them because what's good about it is that they have the same x. You see, this one has x to the power n minus 2, and this one also has x to the power n minus 2. So we're going to be able to factor that x to the power n minus 2. But since we have to do this one more time, and you know what? We could do this directly, actually. Now I think about it. Replace n with n minus 2 directly, because that's faster, obviously. This is just taking longer. So let's go ahead and fix it. N minus 2, n minus 2, and n minus 2 everywhere, okay? And of course, that's just going to change these numbers slightly. This is going to be a 3. This is going to be an n minus 2. And then this is going to be an n minus 2. And this is going to be an n minus 3. Because remember, it was already an n minus 2. We had to subtract one more. Okay? So far, so good. Now, let's go ahead and consider the adding the second and third terms, maybe, because they can be added. So here's what we have. Ignore the first term. Let me just show you what this looks like. Otherwise, this is going to be a super long video. I know some people are going to be, they're not going to like it. But anyways, this is the second term. After doing this, wait, I did it twice to the first. No, actually, this is the first term. And then I will add the third. Okay, I can change this too, but let's just add these 2, 3. I just want to show you what this is going to look like. Okay, so, and then I'm going to bring in the, so I'm adding the first and the third, okay? Which is kind of weird, but you get the idea. N equals 3 to infinity. And then this will become n minus 1, n minus 2, an x to the power n minus 3. Now what we can do is they both have the same index to start with. So we can kind of put them under 1 like this. And then what we need to do is take this out so we can factor this out and just worry about the coefficients. So what do we have? We have n minus 2 times a sub n minus 2 plus n minus 1, n minus 2, an. Now this is going to be, the giant thing is going to be the coefficient of x to the power n minus 3. Now let me tell you what happens after this, right? On the left-hand side, do we have x to the power n minus 3? Absolutely. If you also change the index here, you're going to realize on the left-hand side, we can also do the same thing. I mean here, you can basically replace n with n minus 3 everywhere, and then you're going to be able to compare those coefficients, okay? So anyways, that's just low power mode. So you get the idea, hopefully, right? Let me go ahead and show you the second method because I think the second method is really, really, really cool. Okay, so here's our equation. Because of the way these powers are added, I mean, not the powers, but more like the derivatives or different orders, right? We're going to assume that, okay, our solution is supposed to be in the following form, like e to the power something. So we're going to assume that, okay, can our solution be something like e to the power kx, where k is a constant, right? Why does this work? Because we're adding the derivatives and it's equal to y. So it's kind of like a linear scenario, okay? So let's go ahead and take this and differentiate. If you differentiate it once, it's going to be k e to the kx. If you differentiate it twice, it's going to be k squared e to the kx. And then if you differentiate it 3 times, it's going to be k cubed e to the kx. You see, the e to the kx is always going to come up on both sides, which will cancel out. And we're going to end up with a polynomial. That's the whole idea. In other words, we're using the characteristic equation here. Make sense? Of course, this will go on forever, but let's go ahead and make the replacements. The first derivative, remember, k e to the kx. And then we have the k squared e to the kx. And then the k cubed. And now you got yourself a really, really nice pattern. If you take out e to the kx, here on the right-hand side, you're going to get also factor k out, 1 plus k squared, go on forever, and that's an infinite geometric series, which is awesome, right? E to the kx cannot be 0, so it'll cancel out, leaving us with 1, and now we got the following. And guess what? Our goal is to solve for k, and you're going to get a really cool answer from here. But if you remember the formula for the infinite geometric series, this turns into k times 1 minus k over 1 minus k squared. Wait a minute, is that correct? No, I don't think so. It is actually not that. It's 1 over 1 minus k. I don't know what I'm talking about. And this is equal to 1. Great. What does that mean? It just means that we're going to cross multiply, and that gives us k equals 1 minus k, and from here 2k equals 1 gives us k equals 1/2. So clean, right? K equals 1/2 means y equals e to the power 1/2 x is a solution, but guess what? If this is a solution, any constant times this is also a solution. So we're going to write the general solution as c times e to the power 1/2 of x, and this will satisfy the equation. Now, what would happen if you continue with the first method? Hopefully, you would get a series that would resemble this. Who knows? And this brings us to the end of this video. Thank you for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time in another video. Until then, be safe, take care. Don't forget to check out aplusbi, which is my channel, focuses on complex numbers. And I'll see you next time. Bye-bye.